Okay, folks, these are the answers to the Systems and Connected Objects review for the points over points. So, answer to question 1. You have 3 objects. It's frictionless. The only outside force is this. And then they draw you, instead of drawing you the force diagram for the entire system, they draw you the force diagram for each individual object. And what I want you to note is by Newton's third law, the internal tension between 1 and 2 is the same, and then the internal tension between 2 and 3 is the same. And then they say, given that each mass going from left to right is a little bit bigger, how does the force and the string tensions compare? So what I want you, the reason I chose this is what I want you to know conceptually is this force's job is to accelerate everything. Because if you looked at the system, all of these green forces cancel, and the acceleration of the system is just the outside force over m1 plus m2 plus m3. So that force must be the biggest, because it's accelerating everything. The second tension, if you lumped these two together as a system, then these two forces would cancel, and tension's A job is to accelerate M2 and M3. So since it has less work to do, it is a little bit less than the outside force. And then tension 3's job, or TB, its job, if we focused on just the third object, its job is only to accelerate M3. So it has the least work to do of all of them. So that is your relationship. Okay, if you ran the numbers, which I know there's a question from your homework with 3 blocks, you would get this. We had to find the normal force to have the tension. But the correct answer is, which is kind of backwards here, is A. This is the biggest, and then A, and then B. Okay, question 2. And it's frictionless, so on the test I would put this on wheels, so you would know this, but you have the outside forces of the weight of the sphere and the weight of the block, but part of the block is pushing into the incline, balanced by the normal, and part of the block is pushing down the incline. Only the mg sign is what makes it slide. Okay, so you are likely to see an incline again. It's maybe not likely, but it might happen. So in order to accelerate, in order for the system to be going this way, what you need to compare is not the 2 weights, but the mg sign component of m1 to all of the weight of m2. So that is, so in order for them to accelerate down the incline, m1g sine theta has to be bigger than m2g, and then since g is in both terms, you can cancel that out, and that's why they wrote it this way. All right, question 3. 3 blocks attached with strings. This one is not frictionless. So they tell you T1 and T2 are your internal forces. You've got 3 frictions that are not the same because we don't know that their masses are the same, pulling back, and the external force F0 pulling to the right. And that combination of forces is causing an acceleration A. And they wanted you to know, they want you to find what T2 is. This question is from the last new version of the AP, which was super wordy. I'm hoping the next version of the AP in 2025 is going to be not quite as super wordy, but we'll see. So I chose this to give you some practice with that. So they want you to look at T2. Look at this is in terms of M2. All of your options are in terms of M2. So this isn't really a connected objects problem. It's only a connected objects problem in that part of your job is to figure out, am I looking at all three objects, any two combination that are connected to each other, or a single object. And if you look at the options, what they want you to look at is clearly object M2. So if you draw the external forces on M2, you have T1, you have T2, you have friction, and then you have weight and normal that balance each other out and are perpendicular to the motion, so we don't care about them. So they want you to find T2, but it's not clear that you should just know, oh, T2 equals this. What formula is that? It's not. We're still going to isolate M2 and say all of the forces on M2 equals its acceleration. So what do we have? We have T1 going with the acceleration, so that's positive, minus the friction on object 2, minus T2. We're only looking at M2, so that's the only thing in our system, so that is A. We're going to leave A as A because it's in the answers. And then we're going to solve this for T2. So I'm going to bring that over to this side and M2A over to that side, and you get T2 equals, so I'm kind of like pulling it over to that side, but then putting that side over here, equals T1 minus F2 minus M2A. So we're close, so the last thing we have to do is recognize that T1 is okay, that checks, minus mu kinetic because it's moving, the normal equals the weight, M2G minus M2A. So it's a little bit sloppy, but basically the tension is positive for all of them. Okay, that's cool, that makes us feel good. Minus the friction, so that knocks out this, minus the M2G. I'm sorry, minus the M2A, that's an A, not a G. So that knocks out this one, and so the answer is B. So again, a little bit convoluted, but I wanted to put that on the practice instead of on the actual points over points. So I think I have that one right. All right, question 4. They love to do this on the AP, is what is the acceleration of the 0.5 kilogram block? It's a trick question in a way, in that it's the same both blocks have the same acceleration in terms of magnitude. So they're trying to get you to focus on one object, but it's really a connected objects problem. So 0.75 is accelerating down. So on this side, down is positive. Oops, sorry. But on the other side, up is positive. Okay, then let's draw our external forces is the weight of this object and the weight of this object. And you have, let's see, you have tension, which is an internal force, so it cancels. Okay, so basically this is just saying what is the acceleration of the system. And so we want the sum of the forces that are parallel to the motion over the total mass. So we have M1G minus M2G over the total inertia of the system, which is 0.5 plus 0.75. I'm going to quickly talk about some common mistakes people make. Your denominator is the sum. Mass does not have direction. The denominator should never have minus signs in it. This brings inertia to the system. This brings inertia to the system. Adding mass just is going to slow everything down. So the denominator is always adding all the masses. The numerator, in this case, the weights are competing, but if the system instead were, if the 0.5 was on a table and the 0.75 with a pulley system and the 0.75 was hanging over the edge, you would not subtract this guy's weight because this guy's weight is perpendicular to the motion. So be really, really cognizant of when the weight is in your numerator and when it's not, and why. For this system here, let me do a, I guess, markup. For this system here, you take a highlighter and you trap both of the weights are parallel or anti-parallel to the motion. In this system over here, you are only trapping the weight of the 0.75 kilogram, but the weight of the 0.5 kilogram is perpendicular to your highlighter. So that's why it's not included. Okay, I know you know how to calculate weight, so what you get is 7.35 newtons pulling it clockwise, minus 4.9 newtons trying to pull it counterclockwise, and losing over 1.25 entire kilograms of inertia, and you get an acceleration of 1.96 meters per second squared. In previous years, like in the 80s, you did not have a calculator on the multiple choice, so they often said, like, most nearly, they rounded G to 10, and so 1.96 is close to 2. So some of the multiple choice, if you're finding questions online or have a study book, if you get close and it involves gravity, sometimes they round that to 10. Okay, I think this is the last connected objects problem. So you have an outside force pushing on two blocks, and the surface is frictionless, so pretend like these are on wheels. What is the normal force between the two objects? All right, they're asking you for an internal force. So what I'm going to do is I'm going to show you the logic way to do this, and then I'm going to walk you through the math way to do it, the long way to do it. Okay, so similar to the very first question, the applied force's job is to accelerate all 7m of inertia. Because the 3m has inertia, when the applied force pushes on the green object pushes into the pink object, causing a normal. I'm going to call this the normal on the 4. And by Newton's third law, the normal on the 4 causes a normal back on the 3 that is equal in magnitude and opposite in direction. Okay, so I really, really want you to understand that, not just memorize it. The applied force squishes the 4 into the 3. Those molecules are compressed. They cause this normal force on the 4. By Newton's third law, there is a normal force as well on the 3. And these two cancel, which is why they don't affect the acceleration of the system. So the acceleration of both objects is caused by the applied force. But we want the magnitude of this internal normal. If we look at the whole system, it will cancel, and we can't get that. So what we have to do is isolate the 3m and say this internal normal is causing just the 3m to accelerate. Well, that is 3/7 of all the mass. So the internal force is 3/7 of the applied force in this case, because what's in front of it is 3/7 of all of the mass. Okay, so that's a great trick, again, especially if you are taking the AP. Some of the questions are really logic problems that they don't want you to take the time to do, but I will show you how to do this problem out the long way. So the first thing you do is find the acceleration of the system, and that is just the force applied, because that's the only outside force parallel to the motion. I'm not drawing the weight in the normal, over 7m of inertia. Okay, that is the acceleration of the system. To find the internal normal, we could look at the 4m, and we would say FA minus N4 equals 4MA, and you would get the same thing. So much easier to look at the 3m because the only force acting on it is the one that we care about. So if we apply Newton's second law to only this, define this as our system, then the internal normal equals m, which of our system, which is just 3m, times a, which is the applied force, over 7m. And then the mass cancels, and we get that the N3, which is the same as N4 in magnitude, is 3/7 of the applied force. All right, hope that makes sense. All right, question 6, the first of these circular motion questions. You got a 4 kilogram mass, 2 meter long rope. So it wants to fly off tangent, and the weight is always down, and tension is always pointing towards the center of the rope. So both of those forces at the top are radially inward. So in our radial column, we're going to say that forces are helping me turn. Both forces are working together to turn it. So the tension in the rope, which is what we care about, is equal to mv squared over r minus the weight. All right, and again, I want you to get more and more comfortable using just variables because it's a great skill. And think about what these things, it helps you see what things mean, right? If you have numbers in here you can't see anymore, like, oh, tension has one job, or tension has a job to turn me, mv squared over r. But hey, I'm getting an assist from gravity because it's also pulling in. So I don't have to do all of that work. I'm going to subtract the weight because the weight is helping me out. So the tension doesn't have to work as hard. Okay, that is the advantage of not having numbers, as you can see what all of the different things are doing for you in the system. Okay, so now we can plug in numbers. We have 4 kilograms times 5 meters per second squared over the radius, which is 2, minus the weight, which is 4 times 9.8. Okay, so again, this is the force needed to turn it, but, oh, I got an assist from gravity, so I don't need to work. I don't need to cause all of that. I don't need to work 50 newtons. If this were on a table and gravity weren't helping me, then the tension pulling in would have to be 50. But, oh, gravity's helping me with 39.2 newtons, so the tension in the rope is reduced to 10.8 newtons, which is B. Okay, now we have a gravitron ride, and the person, what's a little confusing is, from a bird's eye view, if you looked at the person, their speed is tangent. So they're kind of, their speed vector is kind of going into the page right here. That is the speed that they and the ride have. Okay, so classic problem. The Earth is trying to pull them down. They are touching a surface. That surface is against their back, so it's pushing them radially inward, just like the racquetball, right? That's what was helping the racquetball go in a circle, was running into the hula hoop. Without friction, they would clearly slide down the wall, and so the nooks and crannies catch, causing static friction. So even though they have velocity, the velocity is not relative to the wall behind them. The velocity is relative to a person standing on the ground and seeing that they're moving. Relative to the surface, like the frog on the piece of foam, they're not moving relative to the surface, so this is static friction. All right, so this is why I think it's helpful to think about, this is the plane of the circle that they're going in. So in my radial column, I only have the normal helping me go in a circle. So that should make sense. The faster I go, the harder the normal has to work to turn me. The more inertia I have, the harder the normal has to work to turn me because I have more inertia. What's not as clear is the bigger the radius, the less circular the circle is. The more it is like a line. So the tighter the circle, the harder it is to turn, because you can see going around this curve, I'm going to turn faster than going around this curve. Okay, so that's my normal. This is a little bit tricky in terms of variables and what you're solving for. We're looking for V. So if we just solve this for V, we'd get V is the square root of NR over M. Okay, oops, that's not very rewarding, but we haven't dealt with the non-radial column yet. Not sliding means my acceleration is 0. The forces are balanced. So that means static friction equals the weight. What is static friction? It is mu, that's good, times the normal. And then that's why we looked at the radial, because the normal is a function of the speed. The faster you go, the more you're slammed into the wall, the greater the normal. Okay, and then mass cancels, which is great. So it doesn't matter if it's a little kid or a big person on the ride. We want to solve this for V. So we get V squared equals RG over mu. So V is the square root of GR over mu, which is option A. Okay, moving on. We have a 500 kilogram roller coaster going over a hill of radius 15. The point B kind of got cut off. What is the maximum speed the car can have and still remain on the track? So up to now, max or min triggered static friction. It's still what's called a critical point in math or physics, but it's not about static friction. It's about not falling off. So let's look at that roller coaster at the top of the hill. A split second earlier, they were trying to fly off tangent this way. The weight of the coaster helped to turn them because it was pointing radially, partially radially inward, but at 12 o'clock, all radially inward. And since they're touching a surface, there is a normal force. Do not fall into the trap that the normal equals the weight. The forces are not balanced because they're turning. In must win. So since mg is in and n is out, mg is going to be positive and the normal is negative. But the other thing you must memorize is remaining in contact means there is a normal. So that's what the maximum means, is that the normal is on the cusp of being 0, and then if I went any faster, the normal would be negative, meaning I'd lost contact. Okay, so the max min means I'm going to set this equal to 0, and that's kind of my don't go faster than that value. Okay, so we only have radial forces here. And I suggest you draw the normal, because frequently in the problem it's like, hey, what's the fastest I can go? And then they'll modify and say, okay, go half that fast and find what the normal is. So I prefer that you draw a normal and then say, okay, I'm looking at the condition that the normal isn't there. But if it were there, that would be the direction. But it wouldn't be technically wrong if you didn't draw the normal because it's not there. Okay, so radially, it's mg equals mv squared over r, and actually, technically, it does not matter what the mass of the coaster is. All of the coasters would fall off going that speed. And so the speed is the square root of gr. If you do enough of these problems, you will see this equation over and over again. Please don't memorize it, because I want you to know where it comes from and derive it on the test. So please note, this is not like doing, I don't know, like normal on an incline so much that you can just normal equals mg cosine theta. I want you to be able to draw a force diagram and figure out where it comes from. Okay, but the answer is D, 12.1 meters per second. If you go slower than that, you would have mg minus n, and you would find a value for n. If you went faster than that, you would get n equals mg. If you go too fast, this term is too big, and you'd get a negative normal, which means, oh, you guessed the wrong direction for the normal, and if the coaster had wheels below the coaster, then the negative normal means those orange wheels are pushing up into the purple track, and the only way to go that fast is if the track is actually pulling you, helping you to pull in, because you're going so fast you want to fly off tangent. Okay, hope that makes sense. Okay, final problem, and then there's 3 related questions. So you have 2 kilogram mass, radius 0.5, particular speed, the force on the mass by the string. So it's a horizontal circle. It's a side view, so the only centripetal force is the tension. So tension, this is a little bit plug and chug, but I wanted to do the rest of the problem. So 2 times 4 squared over 0.5 gives you a tension of 64 Newton. Yeah, 64 newtons. So that is the tension in the rope. Question 10, if the speed doubled, so you can do the math out and plug it in with the speed being 8, but again, a really good skill in physics is to say, oh, my velocity is squared. So if I double that, if I put in twice the value that I had before, since 2 is squared, it's 4 times what I had before. So it is 4 times as great because the velocity is squared. And again, I think that's just a great skill in quantitative problems because it means doubling one quantity gives you 4 times another quantity, and I think that's important to know. Oh, that means that quantity is really important. Okay, but you can run through the math, but I think it's a good skill. Okay, and then the last question. If the radius were bigger, so I'm going to keep velocity the same, but I'm going to double the radius, then what you see is you get a half of what you had before. And so the tension is cut in half. Because if, let's see if we have room, because if I'm going around a tight circle, then I'm going from, heading north to heading south twice as fast, because it's a factor of 2, twice as fast as if I'm going in a bigger circle. If I double the radius, the time it's going to take me to turn 180 is going to be doubled. And so I only have to work half as hard because I'm not turning as quickly. All right. Hopefully that was a great review for you of both connected objects and circular motion. And thanks for listening.